The next topic in electricity is something called Ohm's law. So we know that we can have the flow of electricity in a simple circuit, and we can have current. In order to have current, we have to have a complete circuit, we have to have some voltage supply, and in general, there's also some resistance to the flow of electricity. So we want to know, how are these all connected together? And it turns out that they are connected together according to Ohm's law. So the amount of current in a circuit is directly proportional to the voltage that's applied. So, what is your battery voltage? And it's also inversely proportional to the resistance. So all components that are connected in your circuit have some resistance associated with them, and so the current is inversely proportional to the resistance. Larger resistance implies less current flow. Right? So like the filament in the light bulb has a certain amount of resistance. If you connect it up to a battery, you put some voltage from the battery, some resistance from the light bulb, and then you will get some current that's flowing through that circuit. Traditionally, we actually write Ohm's law as V equals IR. In other words, we multiply both sides of the equation by the resistance, and we write it this way so that the voltage in the circuit depends on the current that's flowing through the circuit and the resistance. So we could look at the PhET simulation, and we could answer a few different questions using that PhET simulation. What happens as the voltage from the battery increases? What happens to the current? So I'm going to go ahead and I'm going to pull up this PhET simulation. Let's go ahead and do that. So here I have a simple set of batteries here where I have voltage, and then there is some resistance in the circuit, and in this case it's the voltage is 4.5 volts, the resistance is 500 ohms, and then I have a certain amount of current flowing through that particular circuit. So the question is, over here, is as the voltage from the battery increases, what happens to the current? So, and then we also want to know, as the resistance in the wire increases, what happens to the current? And let's go back to the simulation. So here we go. So as I increase the voltage, I'm going to have the voltage go up. Let's see what happens to the current in the circuit. So here's my current, it's 9. As the voltage gets bigger, the current also gets bigger, right? So the voltage was 4.5, the current was 9 milliamps. Now the voltage is 9 and the current is 18 milliamps. So the voltage and the current are directly proportional to one another. All right, I'm going to put this back down. All right, so now I have a voltage of 3. Let's see what happens when the resistance increases. Let's look at what happens to the current. So as the resistance gets bigger, the current actually gets smaller, right? This current value decreased. So the current and the resistance are inversely proportional to one another. As the resistance gets bigger, the current becomes less. So I doubled the resistance. It was 500, it's now 1,000, and the current decreased by a factor of 1/2, right? So if I go back to what it was, can't get it exactly. So around 500 ohms, the current was 6. If I double that, the current decreases by a factor of 1/2. So doubling the resistance causes the current to decrease by a factor of 1/2. So we now know what happens, and we can see that just according to Ohm's law here, right? So in this case, the voltage and the current are proportional to one another, and over here, the current and the resistance are inversely proportional to one another. So sometimes we worry about electrical shock, and it turns out that the damage from electrical shock is caused by current, not voltage. So you can have very high voltage, but it's not going to damage anything in your body. But it turns out that less than 1 amp of current can actually cause death. So, these are just some pictures of some things. Up here, you've got birds that will often hang out on high power lines. There's high voltage, but there's not a voltage difference. So the birds are okay on a single line like this because there isn't a voltage difference. This particular person is walking up here near some pretty high wires, and as long as they are not connected across a high voltage, then everything is fine. So here's a picture that's not fine. So here, the birds on a single wire are safe. So there's a safe bird. He's just hanging out on a single wire. But then you have a bird that has a large wingspan, and it touches both of these wires. And by touching both of the wires, you get a large voltage difference. And because one wire would have one voltage, the other one would have another voltage. And so you get a large voltage difference, and that can cause a large current, and that can actually cause, death to a bird. But the bird standing on a wire, there's no voltage difference because they're connecting. It's like they're touching. It's like the bird on the wire here is like touching the positive side of a battery. You could touch the positive side and the positive side of a battery and it's not going to do anything. But if you touch the positive side and the negative side, that's when you have some voltage or potential difference. There's a video here. This is a YouTube video that you could take a look at. If I'm not mistaken, I'm trying to remember. I think it's actually a clip from the Jurassic Park movie, and it's an older clip. But it's something that's kind of neat. Now, just a quick story, and it'll be very quick. I was with my husband one time, and we were driving in Richmond, and we were at a stoplight, and we saw these really, really large wingspan birds flying, and I thought, that's very odd, and they were very low. Well, one of those birds, just like this, came into contact with two electrical lines, and there was a huge explosion from the transformer that's on the power lines, and you could actually feel a wave of electricity kind of come and shoot through the car. It was a very crazy thing that happened, but this is actually can happen for something that has a large wingspan. So again, it's okay to touch singlet. I don't suggest anybody do this, but touching just the positive side is fine, but touching the positive and the negative is what can cause the damage, because that's the high voltage which can produce the current. Most plugs actually have a positive, a negative, if you want to think about it that way, or a hot and a neutral, and then a ground. The earth is actually a good conductor of electricity, and so when we have the ground connector here, that's actually connected to the earth's ground, and so that's what the three-pronged outlet is. And you can get, of course, electrical shock from an outlet as well if you were to connect across the hot end and the neutral or the ground, because you're then producing a voltage difference, right? Just touching, again, nobody should touch an electrical outlet unless you know what you're doing, but just touching one end of the ground is not going to cause any sort of problem, but it's when you connect across the voltage difference. And again, I want to reiterate, you should not touch a plug or stick anything in a plug. So if we think about Ohm's law, we can think about it in terms of a water analogy. So Ohm's law basically says that the current in a circuit is proportional to the voltage and inversely proportional to the resistance. And here's a simple picture of that circuit that has a switch in it. The voltage supply here is our battery. Here's our resistance in the circuit. If I close the switch, I will have flow of current in the circuit. So the water analogy is, instead of a battery, you would have a pump, something that's actually going to push the water through the pipes, and the pipes are the wires, and the water is like the electrons. It's what's actually flowing. You would have a valve here, which would be like your switch, which you could shut on and off, and then you have the line where it maybe changed a little bit. This is like a hose, right? Where all of a sudden it gets more narrow and it's longer in here, and that's going to resist the flow of the water through that particular circuit where you can have this pump going all the way around. So that's just, so electrical circuits in some ways can be similar to the flow of water, and you have that sort of analogy, pump being voltage, current being the flow of the water, and then of course changing the resistance is changing the size of the piping that you have. In a similar way for AC, you can have something similar to that. Here you would have a pumping mechanism which is causing the water inside that pipe to oscillate back and forth. So by moving this piston back and forth, it's causing the water to go, one way and then the other way, one way and then the other way. And that's alternating current, where there's a vibration of the charge in the circuit. Here it's a vibration of the water molecules. Now you still have to have some power supply here. This is like our pump. And then the resistance would be where that piping just got very narrow and it's harder for that water to get through. So again, just another analogy when it comes to water. All right, let's look at a couple of examples using Ohm's law. Suppose that we have a toaster, and a toaster that has an internal resistance of 30 ohms is connected to a 120 volt outlet in your home. How much current does it draw? Now, I want to be clear, when you connect your toaster to the outlet in your home, the voltage is actually oscillating, right? It's AC. But the 120 here is equivalent to, the AC that you plug in is equivalent to basically 120 volts DC. So it's like taking a 120 volt DC battery and connecting your toaster up. So that's what we mean when we say 120. That's what the equivalent would be for AC. So we know our resistance is 30 ohms, and we know that our voltage is 120, and we want to know what the current is. So the current is just the voltage divided by the resistance. So 120 volts over 30 ohms is 4 amps. 4 amps is a lot of current. Remember, 1 amp of current can kill you. So if you've ever, when you were little, if you have a toaster, your parent may have said, don't stick your butter knife in the toaster to try to get your toast out. Well, the butter knife is made of metal. It's a good conductor of electricity. There's a lot of current flowing through the coils that are inside your toaster oven. Those coils actually heat up because of the current that's flowing through them, and that's what causes your toast to toast. So, so that large amount of current is not unusual in a toaster. Here's another example table where you're asked to fill in the unknown quantities. So for the first example, we know the voltage is 8 volts. We know the resistance is 80 ohms, and we want to determine what the current is. So the current is the voltage over the resistance. 8 volts over 80 ohms is 0.1 amps. In the second example, we're given the voltage and the current, and we want to solve for the resistance. So the resistance, we can rewrite Ohm's law in terms of resistance. So we can cross multiply, bring the resistance up to the top on the left, bring the current to the bottom on the right. And the resistance is the voltage divided by the current. So this is 2 volts over 0.4 amps, which is 5 ohms. And in the last example, we're asked to figure out what the voltage is. We know the current and we know the resistance. So Ohm's law says V equals IR. Current is 0.6, the resistance is 50 ohms, and that gives me 30 volts. So if we have a table and we have 2 of the known quantities, we can always solve for the other quantity in terms of voltage, current, and resistance.